Good morning, champ. Today we're entering the world of ordinary differential equations, the language of change used in physics, biology, and engineering. We'll start with the easiest kind to master, separable differential equations, and finish by solving an initial value problem so we can find the exact curve that fits our starting condition. An ordinary differential equation, or ODE, connects an unknown function to its derivative. A separable ODE is one where you can separate the variables, that is, rewrite it so that all the y terms are on one side and all the x terms are on the other. In general form, it looks like dy over dx equals f of x times g of y. Then we can separate the variables, dy over g of y equals f of x dx, and integrate both sides. That's the key move. Separate and integrate. Here's the 5-step recipe you'll use every time. Step 1, rewrite the ODE as y prime equals f of x times g of y. Step 2, move all the y's to one side and all the x's to the other. Step 3, integrate both sides. Step 4, solve for y if possible. Step 5, use the initial condition y of x naught equals y naught to find the constant c. That last step gives a unique curve that passes through the given starting point. Let's warm up with the classic model. Y prime equals k times y, where k is a constant. Separate variables, dy over y equals k dx. Integrate both sides. Natural log of the absolute value of y equals kx plus c. Now exponentiate both sides to isolate y. That gives absolute y equals e to the power of kx plus c. Using exponent properties, we can rewrite that as absolute y equals e to the c times e to the kx. Since e to the c is a positive constant, we call it a, and remove the absolute value to allow for both signs. That gives y equals a times e to the kx. If the initial condition is y of 0 equals y naught, then a equals y naught, giving y of x equals y naught times e to the kx. When k is greater than 0, it's exponential growth. When k is less than 0, it's exponential decay. Now let's look at a more realistic population model, the logistic equation. Y prime equals ry times 1 minus y over k, where r is the growth rate and k is the carrying capacity. Separate variables, dy over y times 1 minus y over k equals r dx. Simplify the denominator. Now integrate both sides. The integral of 1 over y is the natural logarithm of the absolute value of y. The integral of 1 over k minus y is negative ln of the absolute value of k minus y. So we get the natural log of y minus the natural log of k minus y equals rx plus c. Combine the logs. The natural log of y over k minus y equals rx plus c. Exponentiate both sides. Y equals over k minus y equals e to the rx plus c. Or equivalently y over k minus y equals ae to the rx, where a equals e to the c. Multiply both sides by k minus y equals ae to the rx times k minus y. Distribute y equals ake to the rx minus aye to the rx. Move all y terms to one side. Y plus aye to the rx equals ake to the rx. Factor out y times 1 plus ae to the rx equals ake to the rx. Divide both sides by 1 plus ae to the rx. That gives y equals ake to the rx over 1 plus ae to the rx. Simplify by dividing top and bottom by ae to the rx to get y equals k over 1 plus 1 over a times e to the negative rx. Rename 1 over a as b, and we have y of x equals k over 1 plus be to the negative rx. Now apply the initial condition y of 0 equals y naught. Plug in x equals 0. Y naught equals k over 1 plus b. Solve for b equals k minus y naught over y naught. Substitute back y of x equals k over 1 plus k minus y naught over y naught times e to the negative rx. This is the famous logistic curve. It starts with exponential growth and then levels off at the carrying capacity k. Let's solve a full initial value problem. Y prime equals x, y squared, and y of 0 equals 3. Step 1. Separate variables. dy over y squared equals x dx. Step 2. Integrate both sides. The integral of y to the negative 2 is negative 1 over y. The integral of x is x squared over 2. So we get negative 1 over y equals x squared over 2 plus c. Step 3. Solve for y. Multiply both sides by negative 1. 1 over y equals negative x squared over 2 minus c. Now take the reciprocal to isolate y. Y equals 1 over negative x squared over 2 minus c, which simplifies to y equals negative 1 over x squared over 2 plus c. Step 4. Apply the initial condition y of 0 equals 3. Plug in x equals 0 and y equals 3. 3 equals negative 1 over c, so c equals negative 1/3. Substitute back to get y of x equals negative 1 over x squared over 2 minus 1/3. Simplify that to y equals 6 over 2 minus 3x squared. That's your unique solution curve passing through the point 0,3. When you plot this, you'll see that the curve shoots up sharply as x approaches plus or minus the square root of 2/3. Those are vertical asymptotes, where the denominator 2 minus 3x squared equals 0 and the solution blows up. Between those lines, the solution is smooth and positive. Outside that range, it's undefined. A few pro tips. Always check if g of y equals 0 gives constant or equilibrium solutions before dividing. Keep absolute values when integrating 1 over y, and fix the sign after applying the initial condition. The solution is valid on the largest interval where f and g are continuous and non-zero. Finally, remember the existence and uniqueness theorem. If the right-hand side f of x and y is continuous and satisfies a Lipschitz condition in y, your initial value problem has a unique solution. For separable ODES with nice continuous f and g, this is almost always true. So champ, separable equations are the easiest differential equations to solve, but they already describe many of the most important processes in science: growth, decay, and balance.